You guys are in for a really good keynote today. It's my pleasure to introduce the keynote presentation from Steve Teig. Steve is a visionary technologist and serial entrepreneur whose work has impacted industries ranging from software and semiconductors to biotechnology and machine learning. Steve has served as a founder and/or CTO for multiple companies, and his contributions have been recognized with numerous awards, including an Edison Award and a World Technology Award. Steve is an inventor on over 370 patents across multiple disciplines and a well-regarded speaker as well, who's delivered keynotes and invited lecturers at conferences and universities around the world. He currently serves as CEO of Perceive, which provides the Ergo Edge AI processor, a purpose-built chip to enable large neural networks to run within power-constrained devices for a wide range of applications. So let's give a warm welcome to Steve.
Thank you very much, Rob. Thanks also to the organizers for giving me a chance to present some ideas today. And thank all of you for showing up in person. What a treat. Today I'm going to talk about ideas I'm quite passionate about. I've been working on machine learning for more than 30 years now in various incarnations. And what today's talk is about are really two things. First, I believe that deep learning would be even stronger than it is if we depended less on folklore and anecdotes and spent a little more time on math and principles. And the second thing is that I believe efficiency matters. That it's not enough to make models that seem to work. We want to worry about computational throughput per dollar, per watt, per other things. My intention in this talk is to challenge your thinking just a bit. I'll present some ideas that are probably unfamiliar to you, and likely some ideas that are familiar to you, but I'm hoping you'll think about those in a new way. And I'm intending most of what's in this talk to be technical, but accessible to a general technical audience, with the occasional aside for someone who's a bit more expert. All right, to get started, I think everybody would agree that deep learning is doing some seriously impressive magic tricks these days. From being able to recognize all of the objects in a street scene, something that would have been witchcraft even 15 years ago, to colorize images in a very credible way, to determine the crystal structures of proteins from their sequence, one of the holy grails of biotech, to beat the world's best Go players at Go, to do a halfway credible job of translating from one language to the next, and a halfway credible job of having cars that drive themselves. Absolutely unbelievable. But I also think we need to recognize these for the magic tricks that they are, and not magic. One of the things that have accompanied this development of deep learning and deep learning models is that we keep making bigger, badder models from the previous year. 15 years ago we had 1 million parameters, and then a few years ago 1 billion parameters, and now 100 billion parameters, and then 1 trillion parameters. And where are these ridiculously enormous models running? Well, first they ran on GPUs, and then they ran on racks full of GPUs, and then they ran on buildings full of racks full of GPUs, and then they ran on campuses full of buildings full of racks full of GPUs. What's going on here? I think we've forgotten that the driver of innovation in computing for the last 100 years has been efficiency. More computation per dollar or per watt has been the source of how computing ideas have arisen over the last 100 years. That's what Moore's law is, after all, right? More transistors on a chip for the same number of dollars. The advance from CISC to RISC in CPUs, similarly, to push that efficiency from CPUs to GPUs, and that's on the hardware side. On the software side, the advances in computer science, in improved algorithms, and even on the theory side, the theories of computational complexity, have all been about trying to understand and trying to improve the efficiency of our computing. Weirdly, we're in an age where people have anti-efficiency when they're doing deep learning and brag about how much bigger and more expensive and more power-consuming their models this year were than the ones from last year. The carbon footprint to train one of these big language models just once, which by the way costs about $8 million, is more than 5 times the amount of carbon footprint for driving your car for your entire life. Similarly, The data centers of the world today are already using more electricity than the United Kingdom, and it is expected that those numbers will increase by a factor of 10 by the end of the decade. Our planet can't afford this path. What's worse is that from a technical point of view, these gigantic models we're building, impressive though they are untrustworthy. By being so enormous, by being so over-provisioned, they become untrustworthy because they're capturing noise in your training data and not just signal. I'll show you a couple of examples. So here on the left is a picture of a stop sign, and today's neural network totally nails that that's a stop sign. If you add very carefully constructed perturbation to that image, the noise I'm showing there in the middle is magnified 1,000-fold so that you can detect it with your eye. All of a sudden, the picture looks exactly the same, at least to my eye, but now the neural network is certain it's a yield sign, a pretty scary thing in an autonomous driving setting. Similarly, here you can see what the noise really looks like. You take a stop sign, it's certain it's a stop sign. You can fiddle with the image in a way that the eye can't even detect, and it's certain that this picture is a picture of a flower pot. With these same perturbations, again, multiply 200x in this case, pigs can fly. You can make a picture that's recognized as a pig and it be recognized as an airplane instead. And in more serious settings, like medical diagnosis, which is increasingly being revolutionized by machine learning, you can see there on the upper left is a picture of a normal eye. It doesn't have diabetic retinopathy, magnified the perturbations by 1,000 so you can see them, and it thinks that that eye is diseased and has diabetes. Normal lungs on the left, pneumothorax on the right. The pictures look the same to me. Normal beauty mark on the left, skin cancer on the right. This is pretty scary. How did we get here? Why are our models so inefficient on the one hand, and why are they so unreliable on the other? To me, the most significant reason is that we're depending on folklore, on anecdotal recipes in the place of mathematical principles that we should be using. And to demonstrate some of how I think of this, I'm going to give 3 examples from much of the rest of this talk that I'm calling a myth, a misunderstanding, and a mistake. And I'll talk about each of these in detail in the next few minutes. The myth is that average accuracy is the right thing to optimize. It's what almost everybody does optimize, but I claim it's the wrong thing. Next is a misunderstanding, the mistaken belief that neural networks are great computers, that they're very expressive as computing devices. And finally, the mistake is the mistaken belief that compression hurts accuracy, that we better not compress our models, because if we do, we're going to lose accuracy. Just the opposite is true. So taking them in turn, we'll start with the myth about average accuracy. So before I get a little technical, let me give a motivating example. We live in an era where everybody worries they have COVID. So I've built an AI model that tells you whether you have COVID. And my model says, no, you don't have COVID. It always says no. Well, there are about 18.5 million active cases these days. The world population is about 7.5 billion, which means my probability, the probability of you have COVID is about 0.25%. So my model is 99.76% accurate, and I'm going to win this paper at the International Conference on Machine Learning next week for that, right? Well, not really. My model is totally useless, despite the fact that it has very high average accuracy. And it's totally useless because some mistakes, like dropping a club when you're juggling, don't really matter, and other mistakes are a little bit more serious. And yet, the neural networks we have don't distinguish between serious errors and non-serious errors. They're all scored the same because you're just counting them up. I would claim that this is by no means an extreme example I just showed. Average accuracy is almost never what customers actually want, even though almost all of our models optimize for average accuracy. I have a security camera outside my house, and it's 99.9% accurate in detecting people, except for that time the burglar broke into my house. Not such a good security camera. I have face recognition on my phone, and it keeps everybody out except this guy. I have an autonomous car, a Tesla, and it drives wonderfully on the highway, except that one time a year it crashes into the median and bursts into flames. I hate when that happens. And I have an AI model to predict the stock market, and it works great, except when there's a stock market crash. It's actually not so easy to come up with any example where average accuracy is what customers would actually want for machine learning, even though everybody's working with average accuracy. How did we get here? What happened? I claim that this is an incorrect application of the great ideas of a great man, Claude Shannon, one of the great thinkers of the 20th century. But he worked at Bell Labs, and what AT&T was worried about was optimizing communication networks, right? To optimize communication networks, you do in fact want to maximize the average throughput of the networks. And Shannon brilliantly invented this idea of information theoretic entropy. But what entropy means, it is the average length of a message to communicate a message given a probability distribution over messages. It's the average message length, and that's a great way to compute capacity of networks. In the context of machine learning, that frequently makes its way into cross-entropy, which you can think of as the average surprise. How surprised should you be that the network said cat when this is actually a picture of a dog? That's what cross-entropy is. And there are fancy variations on the theme, like KL divergence, which again is the average surprise at seeing items selected from probability distribution P when you're expecting probability distribution Q. Now, these ideas are fantastic and powerful and deep. They just don't apply to neural networks. What the neural network cares about in real life, almost always, is that you shouldn't ever make a big mistake. Reducing average error is not, in fact, the goal. And if you use things like entropy and cross-entropy, you're optimizing the wrong thing, and that's why your models are getting fooled. And it's not just that the loss functions with cross-entropy are misplaced in working on average. Not every data point is equally valuable either. Suppose I want to build a face recognition application, and I live in Norway, so almost everybody I encounter is white. And there are a few folks that I encounter that are black. So my training set happens to have about 10,000 white faces and happens to have about 100 black faces. Well, let's see what goes wrong. If the average error when I look at a white face for being able to detect it, to recognize it, is error sub W, and the average error of looking at a black face is error sub B, and I add up the error on my entire training set, well, I get 10,000 times the average white error plus 100 times the average black error. That's right, I'm going to cost errors on white faces 100 times as much as I'm going to cost errors on black faces. And I mean, racism is a terrible and horrible thing, but besides racism, we're programming the mathematics in our models to prefer making mistakes on black faces than to make mistakes on white faces. Are you surprised that we do worse on black faces in practice? This is terrible. So how do we get from this myth to a principle to replace it with? On the loss function side, we really need to think about penalizing errors based on their severity, not their frequency, not how often they occur. So cross-entropy, which is practically every place, is not really such a good choice as a machine learning loss function. On the training set, you want to make the influence of each data point be proportional to how much unique information that data point is giving you. So the uniform weighting that almost everybody uses isn't really the right thing. Now, some of you who work on machine learning think, oh, come on, I don't make that mistake. I'm much cleverer than that. I balance my data set, and I make sure that I have the same number of black faces in my data set as I have white faces in my data set. Really? Well, do you have the same number of bearded black faces in your data set as you have white faces? Do you have the same number of bald bearded black faces in your data set as you have white faces? Do you have the same number of glasses-wearing bald bearded black faces in your training set? I'm going to guess not. Balancing ain't going to get you there. You really need to look at how much information each data point is communicating and give it as many votes as that amount of information. All right, so that's all for the myth. Let's move on to the misunderstanding. Most people believe, because of the incredible set of magic tricks that deep learning can do, that neural networks are great computers, that they're very expressive. And there are even theorems to that effect that are oft quoted. Neural networks are universal approximators, and neural networks are Turing-complete. And yes, they're theorems, they're true. But the conditions on which those, and assumptions on which those theorems depend, are very specific and are not, in fact, satisfied by real-life neural networks. Let's take a look. So first, this idea that universal approximators are what neural networks are. What the papers actually say is that you can approximate any continuous combinational function arbitrarily closely with a feed-forward neural network, which, by the way, depends on having non-polynomial activation functions. I will wager you didn't know that. So continuous arbitrarily closely, if that's really going to be true, we need an infinite number of bits for arbitrary closeness, but we can wave our hands about that one. We can get enough precision, perhaps, from our existing computers. More concerning is that the only functions you can build in a this kind of neural network, are combinational, meaning computations that have any state. The idea of memory can't even be represented in a network that looks like that. So when you have a feed-forward network, like most people have for most of the applications that I'm showing and that other people are showing, you're not allowed to have any memory at all. Think to yourself, when was the last time you wrote a program that didn't use any memory? Now, that doesn't mean the neural networks are useless. They're tremendously powerful and useful, but for very specific things. They cannot represent computations with memory. And yet, there are theorems that say neural networks are Turing-complete. Let's look at that. So to remind you, a Turing machine is a finite state machine, so finite number of states, with a tape, with a memory sitting beside it. Informally, for those of you who don't look at this stuff every day, a Turing machine gives a mathematical abstraction for everything you'd expect a normal computer, a PC, say, to be able to do. The point is that with the Turing machine abstraction, as with real computers, if you add more memory, you get more expressiveness. The computing part's over here, the memory part's over here. You can add more memory to be able to handle larger and larger problems. Neural networks don't look like that at all. The feed-forward networks that I talked about before are obviously not Turing-complete because they don't have any memory at all, right? So what that means is that convolutional neural networks for image processing, temporal convolutional networks for audio, attention and transformers for language, Q-learning for gameplay, all of these networks that make the popular press and that you see so much about, none of them has any memory. None of them is Turing-complete at all. The theorems depend on having some form of state and apply to recurrent neural networks like RNNs and LSTMs and GRUs. And they are Turing-complete in a very narrow sense. Let's take a look at that. The fact is, recurrent networks are just literally finite state machines. This picture on the right here is what a feed-forward neural network looks like. You have data that flows through the network and there's no memory anywhere. The clever innovation of recurrent neural networks is that neural networks have registers. You can see here that there's a state element. It has some feedback, and as a result, you can make a flip-flop, a register, a memory. But where's that tape? We need an infinite memory, or the ability to add memory, in order for something to behave like a Turing machine. Well, the authors of the paper proving that neural networks are Turing-complete very cleverly made the wires in the network have infinite precision. Ooh. So that's an extremely clever idea. But our wires don't have infinite precision. The wires have 32 bits in them. Now, I'm going to say something I know is controversial, but to me, 32 is a lot smaller than infinity. And as a result, to think of this as a Turing machine is completely misguided. Let's see what neural networks can actually do, given that they have, in fact, finite precision. Well, the scorecard that one uses for how expressive a computer is something Noam Chomsky developed in the 1950s called the Chomsky hierarchy. He used a different numbering system from the one I'm going to use, but mine is simpler for the purposes of today's talk, so bear with me. At level 0, at the bottom, are regular expressions. That's what finite state machines can express. Note that finite state machines, regular expressions, can't even recognize palindromes of arbitrary length. That is, strings that look the same forwards as backwards, because as soon as the length of the palindrome is bigger than the number of states, you end up not being able to distinguish one situation from a different one. At the next level, above regular expressions, are context-free languages. This is what happens when you take that finite state machine you used for regular expressions and you add a stack. So you have an infinite source of memory, but you can access it only with push and pop from the top. Now, context-free languages are vastly more powerful and expressive than regular expressions. For one thing, they can recognize palindromes, but more interestingly, they're almost good enough to parse human language. So they can certainly parse languages like C and Java and other computer languages, and in fact, the whole discipline of parsers and compilers is dependent on using context-free languages. The next level above context-free are context-sensitive, which is hard to explain intuitively, but basically it allows you to capture more sophisticated linguistics expressions that include things like music and poetry and various technical sequences that are not recognizable with the context-free language. And only at level 3 do we finally get to Turing-complete. The thing is, the neural networks we have, even the RNNs, which have real-world precision, are only finite state machines. There's nowhere to put the memory. So they're only at class 0, and I'm making them class 0 plus because the fact is that as a practical matter, our existing neural networks can count, which finite state machines can't. you do have enough 32-bit wires, you can count to a really big number. So what that means is RNNs are regular expressions that can count. Ooh, that's what grep is. That is literally what grep is. What that means is that today's most powerful neural networks, the ones that beat the world's best Go player, the ones that fold proteins, the ones that are driving your Tesla, all of those are not any more powerful than grep. Seriously. We don't have the ability to add memory anywhere without changing the structure of the network. What that means is it's not possible to take a mainstream neural network and perfectly parse C. They're not even powerful enough to do that, as incredibly impressive as it is that they can play Go so well. We don't really have a useful, workable model for memory in neural networks that looks like a Turing machine or a PC. There are some very interesting theory papers, but they don't translate into practically trainable networks yet. And as a result, in my opinion, we are very far away from Turing completeness still. Now, you see in the popular press these days, are neural networks conscious? And here again, I'm going to be controversial, but I don't think of grep as conscious. That's just me. One other point before I leave this topic. The heavy lifting being done in neural networks is done by the activation functions. So basically, it's a composition of activation functions that are performing whatever computation you want to perform. And the activation function we use almost every place is ReLU, a pair of lines. If the only function you're ever allowed to use for any computation of any kind ever is this, how many do you think you would need to find a dog in a picture or to translate English to Chinese? A whole boatload. No wonder today's networks are so large. At every turn, they're so unexpressive that we need a zillion objects in order to be able to say anything. Okay, so this misunderstanding about neural networks being expressive. Fact is, almost all of today's neural networks, including the really fancy ones that make the popular press, are computing only combinational functions. They don't have any state, they don't have any Turing completeness. The activation functions that they use are very weak, which is why zillions of them are needed to express complicated functions. The most powerful, from a computational point of view, that we have are RNNs and LSTMs, which are not so popular or decreasing in popularity because in practice they're hard to train. And even those more powerful neural networks can only recognize regular expressions, or basically grep, and can't add state, which means that they can't even recognize palindromes, much less do fancier stateful computations. So from there, let's move on to the third part of the talk, the mistaken belief that compression hurts accuracy. I think what we all want, certainly what I want, is to have principled, efficient neural networks, which means two goals. First, you want your predictions to be accurate. You want to find actual structure in data and distinguish structure from noise. And as long as you're doing that, you want to do this in the smallest, with the smallest possible consumption of resources without compromising your ability to find structure. So what does that mean to find structure? What is the thing that distinguishes structure from randomness? How can we tell? Well, math really helps here because the definition of random, or a useful mathematical definition of random, makes it equivalent to the opposite of compressibility. That is, random data can't be compressed because it has no structure. As soon as there's any structure, that allows compression. The more structure that you have, the more compression you can do. So what that means is learning in principle. The idea of inference of structure from data is the same thing as compression. That's what it means to find structure in principle. Fortunately for us, there's a whole mathematical discipline that underlies compression. That's information theory, and information theory can help us to design better principles, better neural networks, better machine learning. So let's dive into that a little bit. What constitutes finding structure? What's a good description of the world? So this guy, William of Ockham, in the 13th century famously said, roughly speaking, that the simplest model is best. The idea really comes from Aristotle, 1700 years before Ockham. But my problem with this is that if only I knew what was meant by simplest and by model and by best, I would be fine. Fortunately, more modern probabilistic and information theoretic ideas give us a way of stating something like this in a more precise and mathematical way. Basically, that any regularity or structure of the data can be used to compress that data. So my notion of model is going to be a sequence of bits, a program I'm going to send to you. If I can send fewer bits, that makes the model simpler, and then the accuracy of the model in some sense will tell us what's best about it. So The more structure I can find, the better compression. Better compression, as you'll see in just a second, reduces the arbitrariness of the choices that today's neural networks make. If we can reduce the arbitrariness in the networks that we produce, that'll help us understand how much we're allowed to conclude given the data set of a given expressiveness. If you make a model that's too complicated with respect to its training data, you're fitting noise and not just signal. Let me show you what I mean. So those of you who work on neural networks are surely familiar with ImageNet. ImageNet is a public data set that has about 1 million images, each of which is in one of 1,000 very specific classes, like collie dog, or cappuccino, or sailboat, or something like that. Suppose I were to assign those 1 million images to random classes. How many bits would I have to send to you to communicate that entire data set to you? Well, I'm going to need log base 2 of 1,000 bits for each one of my entries, and I have 1 million of them, so that's about 10 megabits altogether. However, the typical popular models people use, like ResNet 50, which has 25.5 million parameters, have about 800 megabits. 800 megabits. Since each of those bits can be 1 or 0, with 800 megabits, I can represent about 10 to the 240 millionth different models. That's a big number. And yet, we run our neural network training. Here's my visualization of 10 to the 240 millionth distinct models. And our training picks that one. This is, in fact, is the correct way to recognize dogs versus cats versus helicopters. Seriously? You really think that in 10 to the 240 millionth models, that there's one that you can tell on the basis of your 1 million pictures is the right one? Surely there is at least one other model that's just as good as the one that you picked. In fact, there are a boatload of other models that are just as good as the ones you picked. Well, as soon as I end up having regions all over this space of 10 to the 240 millionth models, all of which have essentially equally good models, in order not to be arbitrary in picking just one of them, I'm going to pick the entire region because I can't distinguish among them for their excellence, which means I've thrown away a whole bunch of my 800 megabits. That's compression. What just happened is it takes me many, many, many fewer bits to figure out the swath, the region of space that actually captures my data, versus the number of bits it took me to pick one very specific model in this unimaginably gigantic space. The fact that we're carrying all these other bits around and are thus being ridiculously over-precise in what models we pick is why our neural networks are so easily fooled. This explains why pigs can fly and so on, that you can modify a model by taking advantage of all the noise that's in it. You can trick it because it's made so many arbitrary choices in addition to the non-arbitrary choices. So can we do better? We can. What would perfect compression look like? I do not mean the ad hoc techniques that are oft-cited of, well, we can use 8-bit weights instead of 32-bit weights. That's a good idea, but you should do that in a principled way. The popular papers to do this, if you read them carefully, are quite heuristic and arbitrary in their character. And yeah, they're able to get 8-bit weights, but why those 8-bit weights and not a different set? Similarly, you see new network architectures published all the time with handcrafted ways of squishing the network into a smaller network. Okay, you know, their heart's in the right place, but I'm not convinced that these are principled bases for making smaller networks. Fortunately for us, the idea of what is the best possible compression has been mathematized. It is, in fact, capturable by the shortest computer program that can generate your data. That's the smallest representation that's possible. That's called Kolmogorov complexity, and the guy who came up with it is another of the giants of 20th century thinking. This is Andrei Kolmogorov. And what he said is, okay, I have some message I want to send to you, but I know you have a computer. So if the data is random, I'm stuck. I'm just going to send you the data. As soon as there's structure, like, say, the digits of pi, instead of sending you 3, 1, 4, 1, 5, and so on, what I'm going to send you is a program that says, that computes the digits of pi. You can run it on your computer, and you can generate the trillionth digit without my having to send you a trillion bits. This is what it means to find structure. If there is structure, you can capture it with a computer program. The smaller the computer program, the more you've been able to compress the data. So, unfortunately, Kolmogorov complexity is uncomputable. So actually using literal Kolmogorov complexity is not possible, but This now gives us a perspective on how to make better models. We can now step away from trivial forms of compression that just say, try to make your precision a little bit smaller, and have much more sophisticated forms of compression where we have programs that generate our data and so on. So it gives us a basis of getting 50x, 100x, 1000x compression instead of 2x or 3x compression. So you might ask, is 100x compression actually possible in practice today? And the answer is yes. This is what my team and I work on. We are working on building principled machine learning, and we're working on being able to do aggressive compression, and we are in fact able to provide data center class accuracy with 50, 100x compression. I'll show you an example in just a second here. So what I'll show you next is ResNet 50. This is a 25.5 million parameter neural network that was trained on ImageNet, that is looking at pictures that our employees took and that pictures from the web and so on of objects from all over the place, and tries to identify what category they're in. You can see the green at the bottom with text. The lower left is its best guess as to what the picture is showing, second best guess, third best guess, and so on. The things to notice are, first of all, it does a great job of being able to identify objects, but the second thing is the computing power we're expending, 10 milliwatts. So, the stuff that we're running here is running on this chip. No external memory, no external computation in 10 milliwatts. The I/O you're seeing for 40 milliwatts, that's because we're reading in HD images and projecting HD images to show you the pictures, 20 milliwatts in each direction. But the computation of the neural network, about 10 milliwatts, and we're running at 300 frames a second for the internal computation. Let me show you another example. Here I'm going to show you two giant neural networks running together. One of them is YOLO v5, which is identifying all the objects in the scene and putting bounding boxes around them. And then whenever it finds a person, it sends the crop of that person to a second neural network that does pose. It identifies where all the joints and interesting points of the body are, elbow and shoulder, eyes, ears, stuff like that. And here you can see the guy who actually wrote the app and his son. Is there anything more fun than watching nerds dance? All right. So you can see here too, with two multi-million parameter neural networks running again on our Ergo chip without using external memory, without using external processing, we're burning about 40 milliwatts for these two gigantic neural networks running at 30 frames a second. So it is indeed possible, even with technology we know how to build already, to get 100x, and I think there's at least 100x beyond that. That's what's going to happen next. Okay. We've seen some impressive magic tricks in neural networks. Let's face it, I mean, they're incredibly impressive. Deep learning is an amazing pattern matching technology that would have been seen as witchcraft just a few years ago. With that said, if we look at the tricks underneath that apparent magic, today's neural networks are really quite simplistic computing devices. They're not any more powerful than grep. The popular training strategies are still ad hoc and flawed in important ways. We use very primitive optimizers by comparison even to the stuff that is used more popularly in EDA. We've taken a step backwards to some extent in the optimization technology that's used in deep learning. With that said, and with all of the trickery underneath, in my opinion, there is a piece of actual magic in all this stuff. And that's the fact that astonishingly, deep learning gives us the ability to generate programs automatically from data. In the history of computer science, we've mostly had to build our own algorithms. The idea that you can show a bunch of input-output pairs and have the system generate a program automatically from the input-output pairs, that is absolutely amazing and something we don't want to lose. Now, there might be better and more sophisticated and more principled ways to do this, but it's pretty magical that we already have a technology that can generate programs from scratch. Okay. What was this talk about anyway? I believe that we should make machine learning into a science, which it is not yet. I believe we can make machine learning into a science, but only by deciding to do it. And I think that the starting point for that is to recognize that if you wanted to make machine learning rigorous, see it as compression. What it means to find structure in data is to compress. As a result, highly compressed models done in a principled way will be more predictive, not less. They will ignore more of the noise in the training data and concentrate their representation on the actual signal, the actual structure, and make models that are more trustworthy. We are doing the wrong thing by making models that are bigger and bigger and bigger without regard to their size or their principles. Further, and happily, highly compressed models will consume fewer resources. What that means is, like our Ergo chip, they can be everywhere. They can be in edge devices, they can be in battery-powered devices, and also in data centers, and reduce the energy consumption there. Our planet will thank us for focusing more on efficiency than we have, and it's time we did that and remember the value that efficiency has. So I've gone through this a little bit quickly, but before I step down here, just a final thought. I hope I've reminded you that principles matter, that it matters in the work that we do to replace folklore and recipes and anecdotes. And I tried this on ImageNet and I got 0.25% more average accuracy, so I'm going to publish it. Let's replace that folklore by mathematics and mathematical principles. And the second thing is that efficiency matters, but further, that efficiency has been the essence, the driver of innovation in computing for the last 100 years. It has been the North Star for guiding us in what kinds of computing we want to build. That's never been more important than now. It's not only important to get better models, it's important so that we live long enough to see them and before we melt Antarctica. So I have a wonderful team that is working on these ideas with great passion. If any of the stuff I talked to you about today seemed interesting or like fun, we could really use your help, and I hope you'll come and join us. And with that, thanks for your attention.